You know, every single machine, whether it's the engine in your car or a giant robot in a factory, is constantly talking. It's not using words, of course, but it has a language of shakes and shudders and hums. So today, we're going to learn how to translate that secret language into an incredibly powerful early warning system, one that can stop catastrophic failures before they even start. So let me ask you this. What if you could know with almost perfect accuracy that a critical pump is going to fail next Tuesday at 3 p.m.? Now, this isn't some crystal ball stuff. It's the real result of listening to what our machines are already telling us. It's about preventing millions of dollars in downtime long before it ever has a chance to happen. Okay, so here's our game plan for this explainer. We'll start by understanding the language of machines. Then we're going to follow a single vibration on its journey, from a physical shake to a digital signal and all the way to a final diagnosis. And to wrap it all up, we'll peek into the future to see where this incredible technology is headed next. All right, let's jump right in. We're about to pull back the curtain and decode how the invisible world of machine vibrations can be transformed into a crystal clear warning sign, giving us a window into a machine's health long before you could ever see or hear a problem. Okay, so the fancy term for all this is vibration analysis. And at its core, it's a completely proactive approach. Instead of just waiting around for something to break, we're constantly measuring a machine's normal vibrational heartbeat. This lets us spot those tiny, tiny changes that signal a future problem. Think of it like finding a microscopic fracture in a bearing weeks before it actually fails. The whole process really breaks down into 4 clear steps. First, we have to actually sense the physical movement. Then we have to digitize that raw, messy signal. From there, we analyze its hidden frequencies to find patterns. And finally, we use those patterns to predict a failure. So let's kick things off right at the source, with how we sense that vibration. Okay, step 1, capturing the shake. This is where the rubber meets the road, or I guess where the sensor meets the machine. This is all about the hardware, the very first crucial link in our data chain. So the hero of this first step is the accelerometer. You can honestly think of it as the machine's ear. Its one job is to turn that physical motion into an electrical signal that we can actually measure. This is the exact moment the physical world becomes data. And these things come in all shapes and sizes, from tiny, cheap MEMS sensors, kind of like the tech that flips the screen on your smartphone, all the way to super tough industrial sensors built to survive inside a jet engine. But, and this is a huge but, just having a great sensor isn't the whole story. As this quote points out, if you attach it the wrong way, you can actually create phantom vibrations, signals that aren't even coming from the machine itself. So how you connect that sensor is just as critical as the sensor itself. And that brings us to the 2 main ways to do it. On one side, you've got stud mounting. You literally drill a hole and screw the sensor right in. This gives you a super stiff, direct connection. It's the gold standard for capturing high-frequency vibrations accurately. Then on the other side, you've got adhesive mounting, which is way more flexible. It's perfect for when you can't drill a hole or when you just need a quick temporary reading. The right choice really just depends on the machine and what you're trying to listen for. All right, so we've got our signal, we've captured that physical shake. Now comes the really cool part, maybe the most magical step in the whole process, turning that raw, noisy electrical signal into a digital language that actually tells us its secrets. This is all thanks to a brilliant piece of math called the fast Fourier transform, or FFT for short. The best way to think about it is like a prism for vibration. It takes one big, complex, messy signal, kind of like the sound of an entire orchestra playing all at once, and it separates it into each individual instrument. Each one of those instruments is a specific frequency, and each one tells a unique story about what's going on inside that machine. And this is what it looks like when it's all translated. It's a simple chart, really. The horizontal line, the x-axis, shows us the different frequencies. A big spike there tells us what might be wrong, because a bad gear, for example, vibrates at a totally different frequency than a misaligned shaft. Then the vertical line, the y-axis, shows us the amplitude. The height of that spike tells us how severe the problem is. Taller spike, bigger problem. Simple as that. So now that we've turned that noise into a clear language, we can move on to the diagnosis. This is where we actually read the story it's telling us and use that data to find the exact root cause of the problem. And believe me, the list of things you can find is huge. By reading these unique signatures on the FFT chart, you can spot everything from an unbalanced shaft to worn-out gear teeth, all the way to something as basic as a bolt that's come loose. It's like every single problem has its own unique fingerprint, and now we know how to read them. Okay, so a human expert can look at one of these charts and figure it out. But how do you scale that? I mean, how can one person possibly watch hundreds, maybe thousands of critical machines all at once, 24/7, in real time? Well, the answer is machine learning. What you're basically doing is training a computer to be a superhuman analyst. You feed it mountains of data from the past, and it learns to recognize the incredibly subtle vibration fingerprint of a perfectly healthy machine, and how to tell it apart from the thousands of known fingerprints for specific problems. And there are lots of different tools for this job. A support vector machine, for example, is like a super smart bouncer. It learns to draw the most efficient line to separate the good data from the bad data. A K-nearest neighbor model is more like a detective. It looks at a new vibration and compares it to the closest examples it's seen before to figure out what it is. And then you have something like an isolation forest, which is basically trained to be an expert at spotting the odd one out, those unusual signals that just don't fit the normal pattern. And get this isn't just a one-off checkup. Today's systems are streaming this data to the cloud, live, all the time. This gives you an unbroken, around-the-clock watch over your equipment, lets you analyze trends over months or years, and, most importantly, it can fire off an instant alert to a maintenance person's phone the very second a problem is detected. Okay, so we followed that little vibration all the way from the machine to an alert on a phone. That's pretty amazing. So where is all this heading? What's next on the horizon for machine health? All right, let's do a quick recap of the whole journey, right? We sense the physical shake. We translate the noise into data with an FFT. We diagnose the pattern with machine learning, and then we act on it. That four-step dance, that is the heart and soul of modern predictive maintenance. It's what lets us get ahead of failures instead of just reacting to them. But the story doesn't end there. The next big thing is already here, and it's called explainable AI, or XAI. See, for a long time, a lot of AI has been a black box. It gives you the right answer, like this bearing will fail, but it can't tell you how it got there. XAI is changing all of that. It's creating AI that can actually show its work, which is absolutely critical for building trust and for helping engineers understand not just that a machine will fail, but precisely why the AI thinks so. And all of this leads to a really big question about the future of work. As our tools get smarter and smarter, the skills we need to use them have to evolve too. So I'll leave you with this thought. In the future, is the best mechanic going to be someone who's just as good with a data dashboard as they are with a wrench? It really makes you wonder, doesn't it?